Let us begin our journey in the analysis of AC circuits by looking at a very simple AC circuit, the series RL circuit. These will be our objectives for this module. So we'll define what is forcing function, natural, and forced responses. I will explain the difference between transient and steady-state solution, and we will solve the complete response of the series RL using the sinusoidal forcing functions. Here we have a series RL circuit, and this circuit is driven by a simple sinusoidal source via a switch. And the question here is, what is the response of the circuit or the resulting current when we close the switch? The response here will be a composition of two terms, the natural response and the forced response of the circuit. So first, to come up with the solution of the circuit, we need to know what we mean by natural response and forced response. So what is a natural response? So natural response is that response of the circuit due only to its initial condition without any external source applied. So this response can come from any stored energy in the elements when the switch is closed. So for this specific circuit, this could come from the energy stored, whatever energy stored the inductor has when the switch is closed. So again, the initial condition could pertain to the state of the circuit the moment we close the switch. So if the inductance has an initial energy, we could uh, have a response. So the response may not be zero. So it depends if the inductor has an initial energy or initial current here. So we could get a response. Then we go to forced response. So what is forced response? So this is the response due only to the external energy. So now we have an external energy, but the elements had no initial energy or initial conditions. So whatever response that we get there is what we call the forced response. Uh, Usually we call the external energy source as the forcing function because it forces a response on the circuit regardless if there is an initial energy stored in the elements. Okay, so now that we have defined what is a natural response and forced response, we can now proceed uh, in finding at the response of the circuit with the external energy applied and any initial conditions on the elements of the circuit. So to solve I here, we can apply Kirchhoff's voltage law. So we add all the voltages around the circuit. So this will be the beginning equation. And we know that P here, the applied voltage source, we can replace it by this one. From Ohm's law, we know V sub R to be IR. And P sub L, we know from Faraday's law that it is L times the rate of change of the current that passes through this inductor. So the current here is also I. So rearranging this equation, we will get this first order differential equation. So the solution for this differential equation has two parts. So we have the natural or the homogeneous solution and the particular solution or the forced response. So the natural response is the response without an external source. So we get rid of the external source that will give us this differential equation. Solving for this differential equation will give us this solution. So I won't show the detailed solution. So we'll just state here the solution. So since this is a natural response, let's put a subscript on the solution. So I sub n. Now I at t equals 0 is written this way. So this is the current at the time the switch is turned on. So I at t equals 0. For the force response, so we apply an external source, so that would give us this differential equation. So we assume in solving the force response that there is no initial condition, so we let I at t equals 0 equals 0. So solving for this differential equation, that will give us this solution. So it is combination of sinusoidal and exponential terms. The force response can be arranged to look like this. So we introduce a new quantity called phi, and phi is defined as the inverse tangent of omega L over R. Hence, the complete response is now the sum of the natural response and the forced response. So this is the complete response, and after some rearrangement, we can write it in this manner, where again phi is defined as this one. So the first term here in the complete response, we call this the steady state component, while the second term is called the transient component. So let me give some explanation why do we need to specify what are these components. So for the transient component, from the word itself, transient, meaning this component does not stay, it vanishes over time because of the presence of the exponential term. So this term here keeps on decreasing over time. So eventually this entire term here will disappear. How fast will it disappear depends on R over L here. Now this term is steady state because regardless of time, it is there. No, it doesn't disappear. It is a sinusoidal function. It is a periodic function. So regardless of time, it is always there. It keeps repeating itself. We can further simplify the complete response by uh, giving this radical sign a new variable we call z. So later this will have a name. We call this the impedance of the RL circuit. So that will further simplify our complete response into this formula. We can have a graphical view of the response by plotting the formula for I, and that will give us a graph that will look something like this. So it looks like a sinusoidal function with a little twist at the beginning, and that's because of the presence of the exponential term there, but over time this term will disappear, and therefore that will give us a purely sinusoidal function. Steady state component of the response. So the response uh, becomes the steady state component because the transit component disappears over time. So if we, in fact, if we let t equals infinity, that will completely obliterate the exponential term there, and that would leave us something like this, uh, where we have further simplified this term here as I sub m. So if you notice, this amplitude of the sine function is a current because the unit of this is volts over ohms, which is actually in amperes. So that's why we replaced that entire term with I sub m. In fact, this is the maximum value of the current if we plot the current here. So again, phi is given by this expression, I sub m by this expression. If we plot the steady state value for the response against the source here, it would appear that our I is lagging the source, sinusoidal source, by an amount phi, where phi again is the inverse tangent of omega L over R. Also, if the sinusoidal source happens to have a phase angle alpha, that will result into a steady state component that is almost the same, except that the argument in the sine function has an added term here, so plus alpha. Uh, Again, phi is still given by inverse tangent of omega L over R. And if we plot that, the steady state I against the source, uh, it will still lag the source. The steady state I will still lag the source by the same angle phi given by this one. We have some names for some of the expressions in our complete solution. So for example, square root of RL squared plus omega L squared, we call it the impedance of the RL circuit. The unit for the impedance is also ohms by just looking at the units inside the radical sign. Omega L, which is equals to 2 pi FL, is dependent on the frequency and is also called the inductive reactance of the coil in the RL circuit. So 2 pi FL or omega L is uh, X sub L and also called the inductive reactance, which also has the unit of ohms. So as we have witnessed a while ago, the complete response will eventually be equals to the steady state response. And from now on, we will only be concentrating on steady state responses. So if the problem states that we are required to get the response, so that would mean that we're just getting the steady state response. Unless, of course, if the problem specifies that we have to solve for the complete response. So this is our complete response of the RL circuit. And one way to look at this complete response is that it is comprised of two responses. We have the natural response and the forced response. Another way of looking at it is that it is comprised of a transient response and a steady state response, where the transient response disappears over time and the steady state response remains regardless of time. Let's apply what we have discussed to a problem. So here we have a combination of AC and DC circuit. So before t equals 0, the switch is in position A for a long time. And then at t equals 0, um, we transfer the switch to B. So before they transfer the switch, the circuit looks like a DC circuit. In fact, it is an RL circuit with a DC source equals to 100 volts. And then at t equals 0, the switch is transferred and it becomes an AC circuit, but still an RL circuit. So the question is, what is the complete response after the switch is transferred to B? What is the steady state response? What is the amplitude of the steady state response? Phase angle of the steady state response? And whether the steady state response is leading, lagging, or in phase with the applied voltage E. So to answer this problem, we need to look at the circuit first before the switch is transferred to B. So this is the circuit before the switch is transferred, just before the switch is transferred. So it is steady state. So meaning that the inductor here acts like a short circuit. So this is like a short circuit such that we can get the current here by simply dividing 100 by 1 kilo ohm. So that will give us 0.1 amperes. So this is the current just before the switch is transferred to B at t equals 0. So we write that in this manner. So this is the current just before the switch is transferred to B at t equals 0. So it is like I at t equals 0 with a negative sign on the upper right of the 0. We also need to look at the circuit at exactly t equals 0. At this time, we need to know what is the current at exactly t equals 0. And since the inductor has the behavior that it restrains any abrupt changes in current, whatever is the current at uh, just before t equals 0 or just before the switch is transferred must be the same current at exactly when the switch is transferred to B. That is, the current at I equals 0 at t equals 0 must equal the current just before the switch is transferred, and that is also equals to 0.1 amperes. So this is our formula for the complete response where phi is given by this one and z by this one. From the givens, we have these details, and from this we can compute our impedance, and that will give us this result. We could also proceed to compute for the angle phi, and with the data already complete, we can now plug in all these values and get the complete response. So this one, the first term is the steady state response. This one is the transient response. To get an appreciation of this response, I have here a plot of that expression. So initially we can see that I is wildly varying at the start, but in a very short time that behavior disappears and it becomes a purely sinusoidal function. So we can say that in a short time I becomes the steady state response. Now let's have a second problem. So based on the results of the first problem, let us compute for the impedance. So in, well, in fact, we already computed for that. Let's compute for the inductive reactance, the voltage across R, and whether that voltage is leading, lagging, or in phase with the steady state response. Also the voltage across the inductor and what is its relationship with the steady state response, and of course the RMS values of the voltages across the resistance and the inductive element. Okay, so this is our steady state response, and we've already computed our impedance. So inductive reactance is omega L, and that should give us around 754 ohms. V sub R uh, is simply IR by Ohm's law. So we simply multiply this by R, and that should give us this result. And we notice that it is in phase with I because it is almost the same as I, except that we have a different amplitude. For V sub L, from Paradise, we know that to be, well, this is a small letter VL. So that is L d I dt. So L is 2 Henries. So we get the derivative of I, and that should give us this one. So if you notice, if we plot this one, that will give us a result that will lead I by 90 degrees because of the presence of the cosine function. So remember, if we convert this into sine, this will become 125t minus 37 plus a 90 degrees there. And that clearly gives us an indication that this one is leading I by 90 degrees. RMS voltages, so we simply divide the amplitude of V sub R by square root of 2, that should give us this result, and VL, that should give us this answer. That's it for this video, and for our next videos we will show the steady state responses for series RC and series RLC circuits.